Welcome to this explainer. I'm going to be your expert professor today, and together we're going to unpack the high-level mathematical concepts that are quite literally actively protecting your digital life right now. We're taking a journey from pure abstract algebra all the way down to the bare metal circuitry inside your computer. Here's our syllabus for today. We'll start with the math, securing your data, move into groups, rings, and fields, and then explore Galois and finite fields. After that, we'll connect polynomials to computer XOR, walk through finding multiplicative inverses, and wrap it all up with a handy guide to encryption math. Section 1. The math securing your data, the hidden digital shield. We often take our digital security completely for granted, don't we? You send a text, check your bank balance, buy something online. It just works. But we really need to stop and ask, what exact mechanism is keeping our private messages and banking details locked away from hackers? What actually makes up that invisible shield? Well, the answer comes down to algorithms like the Advanced Encryption Standard, or AES. AES is basically the absolute gold standard for encrypting data. But it doesn't run on magic, right? It's entirely built upon an awe-inspiring, highly specialized mathematical universe known as finite fields. If you really want to understand how your data stays safe every single day, you absolutely have to understand the math that AES uses as its foundation. Section 2. Groups, Rings, and Fields, the mathematical nesting dolls. I like to think of abstract algebra kind of like a set of mathematical nesting dolls. On the outermost layer, we start really broad with what mathematicians call groups. When we add a few more strict rules, we step down into the next doll, called rings. And then, when we add even more specific rules to that, we reach the innermost doll, fields. So every field is a ring, and every ring is a group, but the tools get way more powerful as you go deeper. There's a clear, progressive complexity at play here. In a group, you essentially have one operation, like addition, along with properties like closure, associativity, identity, and inverses. Jump to a ring and you add a second operation, like multiplication. But the grand prize, that's the field. In fields, we can safely add, subtract, multiply, and divide using what we call multiplicative inverses without ever leaving our set of numbers. That means we can essentially divide to unlock and reverse operations. And that is exactly the closed loop of math that cryptography absolutely depends on. Section 3. Galois and finite fields, solving the digital problem. Now, standard math is great, but computers have physical limitations. That's where a finite field comes in. It's simply a field with a finite, limited number of elements. These were specifically pioneered by the brilliant 19th century mathematician Évariste Galois, which is exactly why we call them Galois fields, often abbreviated as GF of P. Because a computer has limited memory, say an 8-bit architecture, it simply cannot handle infinite numbers. It desperately needs a closed, strictly finite mathematical universe to operate within. Think about it this way. If ordinary arithmetic is like a ruler that stretches out to infinity, modular polynomial arithmetic is more like a combination lock or a car's odometer. In modular arithmetic, once you hit the maximum number, the dial perfectly rolls back to 0. This brilliant mechanic ensures that the math fits cleanly inside an 8-bit computer system without wasting a single byte of space or crashing the processor with a number that's just way too big. Section 4. Polynomials and computer XOR. Math meets machine. To actually make this work in cryptography, we have to bridge a critical gap. We treat our digital data as polynomials, where the ones and zeros are the coefficients. But instead of just solving for x like you did in high school, we perform arithmetic modulo p. This specific treatment is what forces our results into a neat, finite box. We are doing polynomial math, for sure, but the coefficients are strictly bounded by that odometer rule we just talked about. But the true magic? That happens in Galois fields of 2 to the power of n, represented as GF 2 to the n. Why 2? Because computers operate in binary, strictly zeros and ones. In this specific field, polynomial addition maps exactly to a computer processor's native bitwise exclusive OR logic, or XOR, and multiplication maps straight to logical AND. This is huge, guys. It means the math doesn't need to be simulated by clunky software. It is baked directly into the hardware's incredibly fast logic gates, making encryption algorithms like AES lightning fast. Section 5. Finding multiplicative inverses, the expert walkthrough. When we compare ordinary polynomial division side by side with division over GF2, we uncover a genuinely beautiful shortcut. In GF2, addition and subtraction are completely identical. 1 plus 1 is 0, and 1 minus 1 is also 0. There are literally no negative numbers to carry over. This drastically simplifies calculating the inverse, making it incredibly straightforward for a computer to process. So, to actually find that inverse, let's walk through the extended Euclidean algorithm together. I know it looks intimidating at first glance, but it's really just a simple loop. By repetitively dividing our numbers and strictly tracking the remainders, we step our way down until we hit a greatest common divisor of 1. When we work that sequence backwards, we can reliably calculate the exact multiplicative inverse. This algorithm is literally the master key that allows us to reverse the mathematical operations and actually unlock our encrypted data.
Section 6, Guide to Encryption Math, your final cheat sheet.
Let's wrap all this up. If you're ever solving finite field problems or looking at how modern encryption works under the hood, just follow this checklist. First, confirm your field order is a prime or a power of a prime. Second, utilize your modular odometer to keep the math contained inside the box. Third, apply the extended Euclidean algorithm to find your inverses and decrypt. And finally, translate your math straight to the hardware's XOR logic gates for maximum speed. That right there is the fundamental recipe for AES.
I want to leave you with this final thought. Isn't it truly profound to consider that our entire modern internet, our banking, and our most private communications all hinge on abstract nesting dolls of finite math devised by Évariste Galois over a century ago? Long before computers were even a dream, the mathematical shield that protects us today was already being forged. Thank you so much for joining me on this explainer. Keep asking questions, and I'll see you next time.